Donaghy and Shikhar, welcome. How are you?
Hey, good to be here again.
Hey Xavier, thanks for having us.
Welcome, both of you. So we've had a day of firsts today. Johnny with his first X post, and Shikhar with your first X space. It's all very exciting.
Yeah, the last time I was here, I think, was my first time ever on X, and we were talking about the history of distillation.
That's right. That was a really good one. So hopefully we're going to have a great conversation today. And I've been reading through some of the work you've been doing, and I think it will be quite an interesting conversation. So got a nice, comfortable crowd. You can speak as you wish. We'll get into it, and hopefully a few more people will join as we go along. Welcome, both of you, to your own topic of DEI, Diversity and Evolutionary Inference for Quality Diversity Search. Let's start with, can you actually explain to the guys out there what that phrase means, and perhaps go on to why you started looking into this topic?
Yeah, maybe I can go first. Yeah, so evolutionary or quality diversity search is like a subclass of evolutionary algorithms, which are a subclass of optimization algorithms. And just like very briefly, we showed that when you use LLMs as part of your quality diversity search, you have much better performance if you use many different LLMs versus replicating the same LLM. Um, and we did it empirically, so it's not rigorous formal math or anything like that. We ran some experiments that we built on top of Jensen's Axel primitive, which allowed us to build up a bunch of different nodes where we hosted different LLMs, and then we ran this evolutionary search. And when we hosted the same LLM with each of the nodes, we found that we did pretty well. And when we diversified the LLMs, we found that we did even better. And yeah, I can give you a little bit of like background as to what all that means, I think.
Absolutely.
So like an optimization algorithm is just like a broad class or like a broad field of computer science where you have some sort of problem and you're looking to find the solution. And so um, you need to look through a whole bunch of solutions to find the one that performs best. So like maybe like a very simple example of that would be you have like some length of fencing, and you want to be able to build a three-walled fence to enclose some of your backyard, and you want to enclose as much area as you possibly can. So you have to try and figure out how long to keep each length or each side of the fence to maximize your area. So that's kind of like a simple example. And in that example, you can probably just brute force and actually analytically solve to find the solution. But in a lot of computer science problems, you can't brute force and look through every possible option to get the best solution. And so you run an optimization algorithm, which has some sort of heuristics that kind of like let you explore the solution space in sort of an intelligent way. And so like one class of algorithms that has a heuristic that allows you to do this are evolutionary algorithms. And those are just like they sound, they try to like emulate biological evolution. And so you start off with a bunch of samples where you think maybe these are a good set of solutions that might have a good optimal that might be close to like the optimal solution that we're trying to optimize for. And you call that your population, just like in biology. And then it's iterative. So each round, with some probability, you create a completely new solution that you kind of randomly generate, or you select one of the solutions from your population and you mutate it. Just kind of like when animals biologically reproduce, they kind of like their genes get mated or mutated, and so you can then get a new sample and you can measure the quality of it, and you can put it back into your population.
So you're guiding the change, guiding the evolution a little.
Yeah, exactly. So like the more diverse your population is, the larger the breadth of search space that you're able to cover. And so you can imagine that if you're like walking across a map, and the best solution is at the far point of the map. You need to be able to get over there as efficiently as possible. And so if you have a population and you drop them all across this map, certain samples will be closer to the best solution than other samples. And so there's just like a bunch of heuristics involved that help you um, um, converge to the best solution by mutating samples of your population, adding new samples to your population, and removing samples from your population. So the fewer iterations it takes to get to that best solution, the better. And quality diversity search is just like another subcategory of evolutionary search, where you specifically are trying to break that map up into a grid space and populate as many different squares or sections of the grid space as possible, with the idea behind that being that like the more you're able to cover, the more likely you will be to find the best solution. And so like lastly, there's been a ton of work lately where this mutation operator that I talked about is actually an LLM. And so you see this thing all the time in your real life. If you ever use Claude Code, or you're hosting your own agents, or they spin off a whole bunch of sub agents, what they're doing is they're trying to cover as much of the search space as possible and get the best answer back to your terminal. And so in this scenario, the LLM that's part of your agent, so if you're using Claude, the LLM is like 4.7 Opus or something. That LLM is the mutation operator that's coming up with new samples, and then the agent that's orchestrating all of your other agents are looking at the solutions and kind of rating them and trying to give you like a ranking so that you can know if you've reached this like optimal solution or not. And just because of the way things work, like when you use Claude Code, for example, and you spin off a bunch of sub agents, those are all going to be hitting the same backend. They're all going to be sending requests to the same LLMs that Anthropic hosts. So you don't have this diversity. And so we showed that if you can diversify the LLMs that your sub agents are hitting when performing this operation, you'll get better solutions.
Okay, so adding diverse LLMs, diverse agents to that structure brings you to the result that you want to get to a lot faster.
Right. Yeah. And I don't know if Shikhar has anything to add to that.
Yeah, maybe I can get into the other question which was asked, which is like why we decided to look into this diversity aspect
Absolutely.
in evolutionary inference. So as like Jensen builds towards decentralized ML, we thought of looking at like what are the core benefits of having a decentralized network, and one of the biggest benefits is that if everyone's running their own models, that means, and if say everyone has trained their own models, that means these models are all really diverse, and that becomes a core strength, which is not really which is only a property of decentralized networks. Like you could have a centralized cluster and you could be running different models in all of them, but then at that point it's just inefficient to bring different models, different architectures, and run them in a cluster. So that was like one of the reasons we started looking at diversity. And it just so happens that having diverse models, as Johnny explained, for this use case of evolutionary inference, which is also related to how a lot of agents work nowadays, Cloud Opus in your terminals, it turns out that if a bunch of them interact with each other, convergence happens even faster, which I think is a great result for decentralization in general.
Excellent. So the decentralized networks that we are working with and working towards actually fit this model specifically well, and will become more and more efficient.
Yeah.
That's fantastic. How did you go about testing it? What were the methods, or the type of tests that you were doing to find this out? Johnny, I'm specifically looking at the digital red queen work that you were referencing recently.
Yeah. So yeah. So like I said earlier, there's like kind of a whole bunch of different classes of evolutionary algorithms, and recently, like Google with AlphaEvolve and Sakana AI with their digital Red Queen work have showed that you can kind of get a benefit from running multiple agents and then also adding in adversity to that. So that in the paper they call it adversarial evolution. And so what Sakana AI showed was that this concept from biology called Red Queen dynamics, which says that in evolution you spend almost all of your evolutionary energy just trying to maintain your position in a hierarchy versus advance, because everyone else in that hierarchy is evolving besides you. So that's like where the adversarial thing comes in. And so they showed that when you're running these evolutionary algorithms, if you're competing against the other samples in your population, you're actually, what you're doing is you're demonstrating these Red Queen dynamics in like a digital setting. And so they came up with a really nice framework for exploring this adversarial evolution in an environment called Core Wars, which has been around for a long time. But what it is it's like a computer game where you write a piece of code, and the code is actually what called a warrior. And then when you simulate the Core Wars, and so the Core Wars engine is kind of similar to the Java virtual machine. There's a virtual machine that runs the Core War computer programming language, and you write your warriors in that language, and then you add them all to the virtual machine, and you let the program evolve through time, and you can rank which warriors do the best because it's adversarial. The goal of the game is to write the warrior that will occupy the most memory space in the Core Wars virtual machine as quickly as possible. So if you write one that's really good, it will knock all the other warriors out and it will dominate the entire memory space. And so Sakana AI built this framework, and they said this is a really nice environment to test these adversarial Red Queen dynamics in a digital environment, and they called it Digital Red Queen. And so we kind of took that to be like the state of the art in this evolutionary search. Like if you want to solve a problem, it doesn't have to be in Core Wars. For example, we played around with evolving Pokemon trainers, but you could do this similarly for solving mathematical problems. You could write up an environment where you want to come up with some novel mathematical proof, and you're going to have different agents propose different proofs, and you can come up with some scoring mechanism that ranks the quality of those proofs. And so you can apply these digital Red Queen dynamics in a lot of different environments, but we decided to stick directly with what Sakana AI came up with, just to sort of show like a nice iterative progression. And so we combined the Sakana AI's digital Red Queen framework with Jensen's Axel communications library, and that allowed us to run the Core Wars environment decentralized and distributed across many different machines. And if you just run that with one single node, you're just reducing yourself to the original baseline, which is the Sakana AI paper. Right. So we were able to just run Sakana's code on a single node and then sort of scale up and scale out from there. And so we started off by scaling out by just duplicating that same node and running many of them. And since the number of nodes is now greater than one, there's a few different ways you can kind of combine the findings. But we took a little bit of inspiration from Andre Karpathy's auto research. A lot of people have built on that and tried to build collaborative auto research where different agents are working together.
Right.
And so we thought the natural progression from there is to say, what if the different agents are competing against each other with adversarial dynamics? So each node can come up with try to produce its best warrior running the digital Red Queen framework, and then they can share those warriors with each other. And when it comes time to actually kick off the Core Wars virtual machine and have the warriors compete against each other, the warriors that your local node and your local LLM have produced will be competing against all the other nodes. So you can directly score them that way. And so we were able to kind of get some nice quantitative metrics about how the system behaves in isolation versus scaling it outwards and using homogeneous LLMs as mutation operators, and then conversely scaling it outwards with heterogeneous LLMs. We're able to show through the core war virtual machine that the solutions from the heterogeneous ensemble outperform the homogeneous ensemble or the ensemble in isolation.
Right.
Sorry, the LLM in isolation.
That's the diversity effect in the title of your paper.
Yep.
The whole thing's fascinating. The whole area. There's so many parallels to various different areas running through my mind. Everything from Axel allowing you to expand everything out to more and more warriors, more and more adversarial conditions, almost an entire full-scale war. Cross between StarCraft and Tron, based on some of the analogies you were using there.
Yeah.
There was also the biological angle, though, is fascinating to me. In a previous life, I was studying wine, and you grow vines in the most difficult conditions possible, forcing them to struggle, and then they produce much richer fruit for the product. It's quite incredible that these creations of these kind of natural parallels, which you've now found through the adversarial conditions and diversity, that sounds very much like human life as it's growing around. If I take it a bit too far there.
No, I think that's like kind of the idea. Yeah, no, I think Core Wars is like super StarCraft coded, which is pretty fun.
Fantastic. How are people going to be able to see? Sorry, Shikhar, go ahead.
Yeah, I was just saying, just on what you just said, Xavier, and also what Johnny was referring to earlier. Like Core Wars is an example of what is possible with such a regime. And that was from Sakana AI, and we were able to build on that. But as you mentioned, like these same principles would apply to a lot of other fields like coding, like math problems. There have been papers by Google and attempts, and they're bringing it to the industry with Alpha Evolve as well, where you're giving it hard problems to solve in the domain of math, science, things which have not been solved before. And it's using similar principles and able to get to a better solution. So really, like the only prerequisite here is to be able to measure performance. And as long as you have a problem where you're able to measure performance, you can do something like this and benefit from diversity, maybe.
Excellent. That actually segues nicely into my next question. I was going to ask, where will people notice these effects as this research continues and makes its way into products or platforms? And where do you want to see it go? What's the imagination look like? I guess that's kind of two questions for you both.
Yeah, maybe you can take it, Shikhar.
Sure. Yeah, this one's a creative one, I guess. So we're already seeing a lot of use cases for this kind of technology and just these approaches. By the way, these approaches have been there for a while. Like evolutionary algorithms have been there for like maybe 50, 60 years or even longer. I'm not sure. But they've been there for a while. People have always thought of use cases which are very limited in a certain sense because these mutation parameters in like historically they used to be very fixed, like you change something very minute about your solution every time. But with LLMs as mutation parameters, it gets a lot more creative because LLMs have context of the problem. They know what they like there's a way that they handle a certain problem, and they're also creative with their solutions. So with that in mind, there have been a few approaches towards straight math. So there have been some unsolved problems which have like for example, what is the best way to multiply matrices, and we thought that we were getting closer and closer to the optimal solution, and the optimal solution had not moved for decades. But then
Right.
there was an algorithm which was built in this evolutionary way, which broke that barrier. Similarly, there's the circle packing problem, which was like we recently found a better solution using these same evolutionary algorithms, and those weren't even looking at the diversity aspect, like those papers which found those solutions. So I would say like the primary use case for something like this would be would probably be like science, like hard science and math problems. But yeah, who knows? If we find ways to measure other things in life, maybe this can be like this can find more applications.
Fantastic. The so reiterating some of the comments you made there, the LLM's capabilities, the things that we find them so useful for at the moment, the context, the access to information, and coming up with creative solutions, that's actually going to accelerate under these diverse kind of conditions. That'd be fair to say.
Yep. Agreed.
Brilliant. Johnny, how about you? Where is this all going for you? And
Yeah.
where will we see it take place?
Well, I think that just, coincidentally, I think maybe information markets are like a really nice test bed for this sort of thing, because you have this intrinsically built-in scoring function, which is with the outcomes of the markets, and also they're natively adversarial. Just like in any market, you don't want to just give away your money. You want to earn money.
You're there to win.
Similarly for the agents. So you can imagine like a scenario of either just openly adversarial against everyone else in the world who's trying to take place in this market, or you could sort of construct and build out your own fleet of agents which compete with each other internally, adversarially, to try to maximize the returns on these information markets. So it's kind of like a nice segue to other things that Jensen is working on. And I think similarly too, because the way these evolutionary algorithms are so iterative, and the way they're able to find novel solutions that the LLMs wouldn't come up with without having the benefit of without the benefit of like this quality diversity search and trying to cover the optimization space as best as possible. You also have a really nice segue and avenue into the field of continuous learning, where you can allow these agents and these models to search and explore for a long period of time, like long horizon jobs, come up with some nice rollouts, and then update their own weights and priors based on their findings, which they wouldn't have been able to do if they were operating in an isolated environment. So I think there's kind of like two nice test beds that you could probably combine together here. And one is continual learning, and the other one is using markets as a scoring function.
Absolutely, that makes a lot of sense. Particularly, I was thinking of the having your own crew of agents external to the people or the agents that you are trading against. Your mix of diversity, how you structure that, how you weight it one way or the other, or how homogenous you go, could be part of your strategy and your edge, in a sense.
Yeah, exactly. Like if you're trying to create an edge, that's a great way to do it. And I also just think that the markets themselves, as they become more agentic and humans become more hands off, are going to demonstrate these red queen dynamics just like very naturally. It'll just emerge there.
And then the evolutionary angle, the agents, diverse or not, will be learning that whole time, and then producing actual market questions that will fit within that framework as well.
Yeah, I think so. Yes, there's like a nice virtuous cycle there.
Incredible, absolutely incredible. Well, thank you, gentlemen. We're just about up to the end there. Any last words for people? Yeah, it's absolutely fascinating topic. My mind is still going around in circles, but I can't spit everything out at once.
No, I don't think there's anything else to say really from my end. I don't know about Shikhar.
Yeah, just say it's an exciting space. So like continue to see what's happening in this evolutionary research space. I think it's really going to blow up this year or the next year.
It really is fascinating. Absolutely enjoying speaking with you guys about it. Thank you, everybody, for coming along. The thread from Johnny with the blog links and the paper links are pinned to the top of the space. Otherwise, you can find them on his account or the Jensen account as you scroll through. Also, the paper, DEI, Diversity and Evolutionary Inference for Quality Diversity Search, has been accepted to be presented at ICML in Korea on the 10th of July, is it?
Yeah, at the Scale workshop. Yep.
Fantastic. Congratulations, guys. Anybody attending the ICML conference and the Scale workshop, make sure you drop in and chat to some Jensen team members while you're there. Thank you again, gentlemen. Thank you, everybody, for coming along. We'll have the recording up shortly for you, and we'll speak to you all again soon.
Thanks, Xavier. Bye.
Thank you. Bye.